Well, good afternoon and welcome to this NITheCS talk, which is a physics talk, atmospheric physics. But it's my pleasure to welcome Professor Hassan Bencherif and Professor Begue from the University of Reunion. It's the Laboratory for Atmospheric Physics and Cyclones, am I right? Yeah. Which is a three-part collaboration between University of Reunion, the CNRS, which is the National Research Organization in France, and the third one is
Meteor,
the French Meteor.
French weather service.
Yeah, French weather service. So without further ado, and they've been Hassan has been in long collaboration with Max Michaelis. So there's been a long collaboration.
19.
Yeah, with ozone studies, okay, so please.
Merci. Thank you. Thank you for coming to this seminar. Just I wanted to say that this presentation will be focusing on biomass-burning aerosol observation and studies in the Southern Hemisphere. But my background is not only that, because we are interested in all the topics like ozone variation in the atmosphere, dynamics of the atmosphere, and so on. But this is the focus we have this last 5 years because of the increase in interest for this thematic. And my lab, as said by Alan now, Laboratoire d'Atmosphère stands for less. It's of course mixed research unit, CNRS University of Reunion and Begue. And for those who don't know now where the Reunion is, it's France in the Southern Hemisphere and Europe as well. So we are just here, small island of about 2,500 kilometers, very small, not habited, not of less than 1 million. Most of people are living on the coast side. Inside the island, there is only nature and volcanoes. So, okay, we started our activity there in Reunion Island by early 90s, actually by 92, and we started by doing some ozone. The first measurement we did is ozone sampling in the atmosphere, because we don't know nothing about the atmosphere in the southern tropics. And then we started the new, the first topic from what I remember was to study ozone change in the troposphere and how it's impacted by biomass burning from Southern Africa. It was already at this period of time one of the focus points. But we did some other studies. By the way, 1 year after the beginning of the lab, I was recruited as a PhD student to work on implementation of a new LiDAR. Actually, the LiDAR I'm talking about is the one that is just above, yeah, just above. And I it was the first LiDAR in the Southern Hemisphere, in the tropics, Southern Hemisphere. So this one was dedicated to drive aerosols and also temperature profile. But by this time, the main focus was on volcanic aerosol, because it was by 92, 93 when I started my PhD. And it was just 1 year or 2 years after the major eruption of the Pinatubo volcano. Pinatubo volcano, which erupted in June 91. And the stratosphere was full with volcanic aerosol. And it was for me a good opportunity to show how aerosols could be used as a tracer of dynamical motion in the atmosphere. Okay, this is a little bit of my story, how I started working with the LiDAR. And then with regard to this, I was aiming to see how these aerosols are moving. But we immediately understood that if we want to assess the aerosol contents in the stratosphere, we need to add other points, because only one point of observation in the Southern Hemisphere is not enough, because we know that this region of the Earth is dominated with large-scale motion, like planetary waves, like seasonal variability, and so on. Then we need to have a kind of network of observation. Then we started by the first collaboration, which just after my PhD and my position as an assistant professor with the University of Natal at this period of time, by 98, and we implemented this LiDAR over there. And this was the first international collaboration we established in our region. And after that, we expand collaboration to Madagascar, Seychelles, Rodrigue, and so on. But recently, we spread our collaboration to Southern America, because we also understood that it's not enough to see what happened here, but only to see how could this continent interact with each other in terms of aerosols. And that's why we are trying to make it as hemispherical network in terms of observing atmosphere, particularly biomass-burning aerosols. Okay, this is Reunion, Madagascar, Southern Africa. You can see here the many observations. This is really the map of the Reunion Island. You can see the initial measurements were implemented here in Saint-Denis, which is the city capital of Reunion Island, and also at the airport. All our radio sending with ozone are launched at the airport, and we do have the LiDAR initially was here, but now we have only chemical measurement in Saint-Denis. All the LiDAR equipment are implemented here on the Lido mountain, which is located at 2,200 meters high. And you can see the observatory here. The first picture, you remember the first picture, it's taken at this place. And the observatory is just here. And you have very nice building, which is equipped with more than 50 international instruments, and all of them are working on continuously. It's like an observatory to assess what could be the climate change in this part of the world from the next decade and from this period of time. Okay, then I will just go from there and try to focus on aerosol. Why aerosol? Maybe aerosol are these particles who are traveling in the atmosphere, but the sources of aerosols could be different. We can find dust particles like dust aerosol, which are very coarse, and you have a very important source which is not far from here, which is Namibia, in terms of dust particles. And you have also a very important source, which is biomass-burning aerosol, urban due to the industrialization or due to traffic, and also, of course, volcanic aerosol. Then, in this part of the world, you may experience all of these kind of aerosol, but the most important for this region is biomass-burning aerosol. That's why I'm focusing on it. And of course, aerosol, they can contribute to the radiative budget. They can be used, they can have impact on global climate change, weather forecast, air quality, and health, and also social impact as well. Then they play a very important role in the atmosphere because they interact with solar radiation, and they can also interact with other components to change their size, to change their nature, so that they may have different behavior according to their age. So that's why we need, and one of the most important things is that aerosols seem that they give the most uncertainty in the climate change model. The uncertainty, and because we don't know much about this, and there is a need to improve this. And when you see, for example, when you see how the fire density, this graph is from Castello Soto which showed the fire density over more than 20 years of continuous observation. Right? And you can see how these fires are distributed all around the world. But you see that in the Southern Hemisphere, the mean spot of fire burning is Southern Africa and also Southern America, but and recently from Australia as well. But we are here nearby the biggest spot in terms of biomass-burning aerosol generation. So we need to, and they have a very large impact on climate and health and so on. So in the Southern Hemisphere, there is a lot of sources or in terms of aerosol, particularly in terms of biomass-burning aerosols. That's why we try to focus on that. And I will try to in this presentation, give you some overview about aerosol measurement. We'll focus on renewable observation, aerosol chromatology over Southern Africa and Réunion, and also a case study from the recent fifth campaign that we made at the Kruger Park before concluding. Okay, how do you measure? We can measure aerosol from ground, from space. We can measure aerosol by using active or passive remote sensing or in situ measurement. You have here many ways. This is the LiDAR actually you have here. This is mobile one, which was deployed during the Begue campaign at Skukuza in the Kruger National Park. And this is the sun photometer, which is just above this building, which is working since 2013 to make a continuous measurement of aerosol optical depth. And this is the LOAC, which is an optical counter for aerosol. And this is the blower, which is also a remote sensing one from the ground. Of course, the idea in working is to combine all these observations and also to add some satellite observation to have an overview of what happened in a different location and to have an idea about how these aerosols are transported from one place to another and to understand what are the mechanisms behind this this trajectory. Okay, this is one example of the studies we made in terms of aerosol observation in Réunion. This is from the publication made by Hassan, based on the use of LiDAR observation. You can see here, for example, the backscatter aerosol extension as observed by LiDAR. The LiDAR is an optical system, an active remote sensing system. It will send laser pulses into the atmosphere, and the backscattered signal is measured at the surface, and it gives you an idea about what is the density of the atmosphere and what quantity of aerosol is there through this, what we call aerosol extension. And you can see from this situation that during this period of time, it was by April, May 2015, you can see that there is a lot of aerosol that comes into the stratosphere, which is not usual. And this is connected to the large-scale transport of the Chilean Calico volcanic plume. Meaning Chile is far from Réunion, and this is observation from Réunion, of course. And due to the large-scale circulation in the stratosphere, this volcanic plume reached the Réunion Island in few days, and we were able to understand at what is the altitude height of this plume and how this plume is changing in intensity and also in the height. As you can see from here, this is the stratospheric aerosol optical depth, as observed by LiDAR in red, by UKZN, which is a satellite in green, and also with the LOAC, which is the content. You have only few points for the LOAC because it's very expensive experience. It's launched with a balloon, and it's at least 6,000 euros per launch, and you might not retrieve your instrument before the launch. So it's 6,000 euros just like that. But for good science, you can see from this measurement that the LOAC before, during the event, and after. They have the same measurement as the LiDAR, as also. And you can see before the eruption here, there is this is the background aerosol situation actually, and there is an increase, then decrease gradually with the time. And this is in concordance with what we observe with the LiDAR. Then we can combine LiDAR, satellites, we can combine many observations in order to understand how aerosols are changing or evolving in the atmosphere. This is another example from a volcanic situation as well. It is due to the what we call what is called the Onga Tonga volcano, which erupted in the Pacific in 15 January 2022. And in few days, same situation, but the circulation was reversed. You see from Chile to Reunion, the circulation was from west to east, and for this one, the circulation was reversed. It was from east to west. I don't know if there's some dynamics people here, but it's due to solar wind in the atmosphere. The volcano erupted by April, May, and the Kalboku, but the Unga erupted by January. And by January, the circulation in the stratosphere is westward. The situation is opposite for the volcano, for the Kalboku, when the circulation was eastward. So this is very important to understand how air masses are traveling from one side to another, and how this could impact the transport of pollutants or aerosols if you want to have a good assessment of that. And you can see from the LiDAR in uranium how this plume is very intense, and what is the altitude range of this plume. It was about 26 kilometers, and how does it evolve, change with time. This is only for one night. We have recorded for many nights. We can see how this plume, this layer of plume, decreasing with the time in terms of intensity and also in terms of height. And then this kind of measurements are very useful to follow up and to understand how this plume could change. And the situation with the Tonga volcano is not similar to Kalboku. Kalboku, it rise a lot of H in the atmosphere, which is it is volcanic plume. But the Onga situation is different because it's a marine volcano, and it injected in the atmosphere a lot of water vapor. And this is very dangerous for the ozone. The water vapor interact and lead to the decrease of ozone. This is, and this is the largest important eruption for the last 20, 40 years in terms of water vapor injection in the atmosphere. And it resulted in ozone hole in the tropics, which is not usually expected, because the ozone hole is usually visible on the Antarctic region and during springtime, not during summer in the tropics. As you can see here, we have here the total column of ozone from OMI, which is a satellite. We have here the same, but from the analysis, analysis. And here we have the stratospheric column of ozone. We just separate tropospheric ozone from stratospheric ozone. I don't know if you know, but most of ozone is in the stratosphere. 90% of the Earth ozone is in the stratosphere. Only 10% is in the troposphere. Then that's what, if we want to assess what is the situation in the stratosphere, since the volcano injected a lot of materials in the stratosphere, then we need to split just to see what happened in the stratosphere. Then we remove the troposphere, then we can see this is mini ozone hole, how it traveled from east to west across the Indian Ocean. 13, 18, 19, 21, 22 January. And it's interesting. Reno is here, and we can see how this ozone hole has transited in the atmosphere, in the Indian Ocean. And here you can see some of back trajectories from high split model, which is a trajectory model, Lagrangian trajectory model. And you can, it's used in order to see the air masses we observe for a specific point where they were few days or many days before. And the ending point is renewal here, and you can see all the air masses over renewal in this period of time has crossed through this place of Unga Tonga eruption, the volcano eruption. So this is made in the framework of one of my PhD students, which he will present his PhD next on 16 June next year. Okay, let's go back now to the biomass-burning aerosols in Southern Africa and the Indian Ocean. This is a comparison between what the situation in terms of fire pixels as observed from MODIS. MODIS is a satellite that is dedicated to aerosol observation and also fires. And this is the situation for April, what we do observe, and this is the situation for September. And it means that there is a large difference in terms of fires activity. And if we take it over the month here on a climatological basis, you can see that we have here in Southern Africa the fire season, which stands from July to October. Yeah, this is no. The fire season for our region here is from July to October. And I just wanted to show you the difference in terms of number of spots of fires that we can observe during this period. And this work, from this, we decide to make a company, a feedback company, for what stands for biomass-burning aerosol campaign, to develop a kind of network measurement over Southern Africa and also in Indian Ocean. And this was made in the framework of our French-South African network called Aerosols. There is actually a program supported by CNRS and NRF that is made as a network between five partners from South Africa and four partners from France, and we collaborate in this framework of this network. Okay, just the key questions we try to respond to in the framework of the Aerosols project. It stands for atmospheric research in Southern Africa and Indian Ocean. It's an international research project, and we have funding for five consecutive years within this program, from French side and also from South African side. And that helped us to try to make research and try to respond to the questions: the atmospheric composition, anthropogenic deposition and health, ozone trend and the effect of UV radiation on human species, biomass-burning, plume and outbreak in the Indian Ocean, aerosol radiative effects over Southern. All this question we try to tackle in framework of our activity. And this is actually from the last evaluation or report we made about this work, and we do have about 20 publications per year in the framework of this project. We have since the beginning. At the beginning, it was by 2012 actually. No, but these numbers are for this period of time. 16 PhD students. Most of them have already finished, and we have. Okay, this is about structure, but let's, and it gives us also the opportunity to bring in new projects like the Protea project. To organize also summer schools and a lot of mobilities in terms of student, master or PhD student, and also change of staff and scientists. The people who are involved or the partners who are involved from South African side. UKZN, of course, which has been leading this project from South African side. Northwest University, Zululand, South African Weather Service, and South African Medical Research Council. And also from our side, 3 universities or 3 CNRS, no, 4 CNRS units last year in Réunion, LISA in Créteil, NRM in Toulouse, and LIRO also in Toulouse. And we have, through this project, we have been able to launch many new projects like NRF, NLC, IUF, CNRS, INSU, all that during this period. This is a kind of network, and in this network we are able to make a new project. This is the idea, to bring new projects into this bilateral project. Okay, go back to science. Okay, this is from the situation, for example, by September 2017, you have this huge number of fires in Southern Africa and also in Madagascar. So there is also a lot of fire activity in Madagascar. But this result in emissions of course, plume, smoke plume, and also other components like carbon monoxide or ozone, because it also contributes to produce ozone in the troposphere. Now, ozone in the stratosphere is quite a good component because it's helpful with to block UV radiation. But ozone in the troposphere is different. It is a greenhouse gas, and it's important to reduce this. And due to this fire activity, we do have every period or every fire season increase in the troposphere ozone, whatever, here in South Africa or in Rio, because of this transport. Yeah, every year from our measurement in ozone here, we do see the effect of biomass-burning season on ozone in the troposphere. And there, I will not show it here, but we have recently published papers showing that ozone in the troposphere in this particular area is increasing. Is there any increase in terms of biomass burning activity, or is also associated to increase in terms of urban and industrial activities? This is still open question. Okay, then you can see that this is the carbon monoxide distribution or concentration in the 1-3 kilometers high, and you can see how this CO, the carbon monoxide, just break outside into the Indian Ocean through the Mozambique Channel and come to this and this that's what we call a river of smoke. Every year we can experience this kind of a river of smoke, but the situation is the intensity and the way this river of smoke takes place, it may change. We don't know actually why, because we can have this river of smoke here or here or here like that. So we need to understand. So how this river of smoke just come, and what could be the impact on all this, because we don't know we don't have a good evaluation about the amount of carbon aerosols that are distributed over this place. And to model or to forecast what could be the situation, we need to increase measurement in terms of aerosols. Okay, that's why we try to bring some response by doing this VBAC campaign during 2002. We implemented LiDARs at different locations, based of course on the LiDAR here, LiDAR in Rio, LiDAR in National Kruger Park, and also based on ozone sound and on Dobson and South spectrometers, and also on sun photometers here and other places. And also this kind of chemical sampling measurement from ground and also from satellite. This you can see the setup of the campaign in terms of sites and also instruments that we have used. Okay, this is some images from the campaign itself with the photometer with the LOAC here in the Kruger National Park with the mobile lidars, UKZN mobile lidar, which is here and here. And also, by the way, during this period of time, we do also some training for students, master and PhD students. Then we every year with SIVA, you have been used to organize a summer school for master and PhD students in order to encourage them to join our team in science. And during Viva campaign, we organized some summer school in Kruger National Park. It was very successful one. And here you can see the LUAC is this instrument here. It could be static at the surface, and it could be flying with a balloon like this one. And from this one, you can see, you can have this kind of profiles. This is aerosol profile in terms of concentration and also size distribution. And you can see most of the aerosol are situated here in the troposphere, but there is also an increase of aerosol in the stratosphere. This is linked to Onga Tonga plume passage over the site. So by this measurement, you can have you can study what happened in the troposphere and also what happened in the stratosphere if you are interested in it. Okay, let's move to the next study. It was about characterizing the type of aerosol we do observe at different sites in Southern Africa. We used 13 years of continuous observation from sun photometers. Sun photometers are implemented at different locations. Windport here, Gugabeh, Buntar, Torias, Durban, and Simons. You see, remember the fire spots. Here we are in the heart of the fire spots, and here we are in the center, not okay. Then and here we don't have, but we may be under impact of fire spots from here for a year. Then we use this continuous database in order to understand what is the distribution, what kind of aerosol we may find at different sites on a climatological point of view. And here, just to explain how this works, here you have a scatter plot with aerosol optical depth versus Armstrong extension coefficient. And according to the position on this screen, you can say what kind of aerosol is it. Actually, for example, when you can here we have clear marine aerosol about 7%, which is here. That means that for the Skukuza site, we have over this period of time we have about 70% of aerosol are from clear marine. Most of the aerosol over Skukuza are biomass-burning, all season together. And there is almost no dust, no desert dust. And the second one is the mix. That means that there is mix between biomass-burning aerosol and other components which are also dominant, about 42%. Okay, this is just to show that we can use sun photometers to have a follow-up with aerosol distribution, to also have access to typing of what kind of aerosol we do observe, and what are the quantities of this aerosol. And also, I will not show it, but we can have also access to the size distribution of the aerosol we observe. But I will just focus on this to try to compare what happened from one side to another.
We need.
Okay, I'm done that. Make it quick. Okay, just to show that according to the site, we have, for example, in Windsport or for Pretoria or for Montour, we have about 80–70% of biomass-burning aerosol there. But when you come to the site far from the fire source, we have very few biomass-burning. Most of the components are for example, clear marine types. So I just go quick. In terms of trajectories, we can see that these are the sites that are involved. We can see that there is most of the trajectories are local. It means local recirculation of the air masses. But not only, we have also impact from here. You see, this back trajectories from Southern America. And depending on, for example, here 37% of the trajectories coming this way, depending on the site. So then it's, if we want to understand the situation with biomass burning or aerosol typing in over South Africa, we need to also to take into account contributions that come from the other side of the Atlantic. This is the data. I will not answer. Okay, maybe I will leave this to you later on, because just want to show here during the campaign what we did. We spotted two extreme events at Tuscaloosa. We can see that the aerosol has increased suddenly by September and by October, and we tried to understand what is the situation. And both situations are not similar. We find that there is some different mechanisms that are involved according to the meteorological situation. Okay, just here to show that all the aerosol we observed over Tuscaloosa by September or October event are 100% biomass burning types. So that's clear. And we tried to see how could we see this event from satellite. And you can see this is total column of carbon monoxide. This is out there also, and you can see that this kind of transport, and with the river of smoke here. Remember, the first picture of the river smoke was here, different. So now it's here. Okay, and for the second situation, the circulation is not tilted like this, but it's sometimes that do like this. For example, Durban was impacted by aerosol coming not from biomass region, burning region, but from this, like this. It comes from the Mozambique channel. Okay. Oh, I will skip this because just other instruments that can help in terms of understanding what is the vertical distribution of aerosols from ground up to the, and this is Calliope. So you can see that the maximum of biomass burning aerosol could go up to 6 or 7, maybe, depending on situation, height. Okay, this is the second situation. We can see that how aerosols can go up to 9 or 10 kilometers. And most of them, as you can see here, are biomass burning types. For the dust and the biomass burning. I will leave it here. This is the synoptic situation, which explain how this river of smoke take place, and which due to the anomalies at the sea surface pressure.
Okay, thank you.
Thank you very much. I will give you a short presentation based on the investigations of measurements that we did with the Begue campaign, in particular from the subfundamental observations. Just a word to explain the motivations why we studied aerosols. As it was mentioned by my colleagues, The first reason is about the huge difficulties about the contributions of aerosols to the relative budget. It's very complicated because when we talk about aerosols, we talk about many particles with different chemical, microphysical properties. And one more is difficult is we have an evolutions of the properties of the aerosol during their lifetime. In this slide, we can see the different state of the during the life cycle of the aerosol. We have the emissions, and we have some microphysical which lead to the transformations of the size of the particles. And the last step is the removal process. We have the two ways, the first one by the sedimentations, and the last one by the wet depositions. It is very difficult for the numerical models to reproduce properly these evolutions because they occur at different space and time scale. And when we have this different process, as you can see here, we have different modifications of the size of the solutions. We have basically we have the three size mode. The first one, the diffusions, the accumulations, and the pulse one. With the different microphysical processes, we have the change of the size distributions of the aerosols. It's for this reason it is very important to drive it to some campaign measurements like we did in 2022, the Begue campaign. And as it was mentioned previously, during this campaign, we observed two significant events. The first, to avoid to be long, I will just discuss about the first event. The first event is river smoke. As you can see on this map, from the reanalysis observations, is the map with the color shading. Is you can see the presence and the amount of aerosols over South Africa. We are at the beginning of this event on the 17th of September, and we can see the hermetids contain aerosols on the east and the west coast of South Africa. And at the 20, you can see the river smoke as the plume was dilated. And on this map, you can see different boxes. This box is the domain that we extract the profile of the aerosol from satellite measurements. And we can see the profile of extensions on this the right panel. And as you can see on this slide, we can see that Joburg and Skukuza were impacted by this event. At a different latitude, just to describe a little bit these figures, that you can see on the red one is the total extensions, and the red one here is an extension due to the smoke. And we can see on this part of the altitude, we have this two curve is the same. In order to this part is due mainly to the aerosol, the biomass-burning aerosols. And it's very helpful to use the reanalysis and the satellite observations, but sometimes we have some difficulties because we have some overlapping of the domain of the satellite. It's for this reason, the ground-based observations is very useful if we want to describe properly the properties of the aerosols over a given site. For this study, we selected 6 stations, as you can see on this map, with this different dots. And on this slide, we can decide host stand photometers. The stand photometers, it tracks the stand, and from this analysis of the solar incoming flux, we can have information about the attenuations of the solar radiations. And by integrations of these attenuations, we obtain the aerosol optical depth. And we can obtain these information at different wavelengths. And we use this information to determine the anomaly in the evolutions of the AOD. It's defined, the methodology is reported here. Here we have the AOD P, which corresponds to the AOD due to the biomass burning pool. We obtain these information by subtractions of the AOD of the background measurements to the AOD measurements. We remove the background to the measurements in order to determine what is the contributions of the biomass burning. And we can see on these figures this AOD plume during the two events. The first one you can see here for three wavelengths here in the UV from infrared. And for the first case to be, we can see that we have a strong wavelength dependence. It's due to the aerosol layer is dominated by the fine particles, which is consistent with the biomass burning plume. And we can investigate it more, the properties of the plume, by the use of the AODP. We use from this information, the AODP, we can determine two parameters. The first one is the Angstrom exponent. The Angstrom exponent gives information about the size of the particles. For the biomass burning and for the value range from 1.4 to 2.2. And we can also use another parameters, the Angstrom turbidity. The Angstrom turbidity gives information about the thickness of the plume and the turbidity of the atmosphere. And if you have a thick or a thin plume. And for the different values, you can determine the different level of turbidity, low, moderate, and high. And for the on these figures, you can see the Angstrom exponent for the different sites, the selected site, for during the period of the first event. And we can see that for all these patients, we have the value contained between 1.4 to 2.4, which is consistent with the presence of the biomass burning. From these observations, we have the confirmation that the passage of the biomass burning covers all species. Now, if you look about, you can determine the passage of the plume over this different site from some photometric observations. Now the question is if it's possible to determine the chronology of the plume over each site. It's for this reason that we make a calculations of alpha and beta parameters for all the sites and for during the period of the first event. And we can see, and we look of these satellite observations, the beginning of the event on the 15th of September, we can see at global level you have values of alpha of 0.7. Is correspond of not very small particles, is a mix of coarse and thin particles. And after on the 16th and the 17th, where we can see from the satellite the arrival of the plume on the west coast near to global level, we can see that an increase of the alpha parameters, which correspond to the passage of the plume. And when we look about beta parameters, we have an increase which corresponds to an increase of the turbidity, or the thickness, an increase of the thickness of the plume, which is consistent that we observe from the top right. And when we move and we follow the trajectory, when we arrive at Pisa, we can see that we have values which consistent with the biomass burning plume. And we can follow the chronology and we can see the aging of the plume from the sun photometers. And we can see Mongu, which is located here. It is not very impacted by the plume, but on the 20th of September, we can see that we have the plume near to these regions. And we find the same result with the sun photometers and which values are consistent with the biomass burning. In conclusion, that it is very useful to have the very good network of observations. If for this first case, we can see that from the sun photometers, we can extract a lot of information about the optical properties of the biomass burning fluid. And the next step of this work is to use numerical tools like as Sexton to fill with emissions inventories in order to determine the contributions of different sources, South America or South Africa, and the variability of the aerosols. We did the same study with monoxide carbon. You can see here the results. The right line is partial column of CO obtained from Begue, and the orange curve is the simulations obtained by Fletcher. And when we discriminate two sources, South Africa and South America, we can see at the beginning of the event, the 17th of September, we have the contributions, the main contributions is due to the South American contributions. And when we move in the time, we can see that the contribution of the South America decreased and the contributions of South Africa increased over the time. And now our job is to perform the same simulations, but for aerosols, by using the sun photometers in order to validate and constrain the simulations. Thank you very much for your attention.
Here we've got a few minutes of questions. Any questions? Yes, Michelle.
Thank you very much.
Well, yes, but they have a very large network of observation.
So they see
They, yeah, they have more measurement, more people are involved in many, all the European countries are involved.
it's not so much to research because everybody's on it. Whereas in the Southern Hemisphere, you've got lots of opportunities.
Yeah.
Not really.
But yeah, the situation is different. That's why I say that we need to strengthen to have more measurement, because we know very little what happened in our, and there's much to do.
Well, I have a couple of questions. Oh, you, sorry. Oh, all right. First, are there observational points in Australia?
This is Australia.
Australia?
Yes.
Because I didn't see the dots in Australia.
Yes, about Australia can talk about the last event of Australia. And you can see this event impact of biomass-burning radiative.
But do you have observatories in Australia as well?
Yes,
Because we didn't see it on your map. Africa, we saw Africa.
Because it's just starting collaboration.
It's not in Australia.
But we have already prepared a paper with that.
That's the other main.
About this, because the fire in Australia are most bigger, yeah. They have the capacity because the peer convection process means that to go up to the stratosphere. There are very lot of energy and starting process. Like a volcanic.
This is also one of the main land masses in the Southern Hemisphere. My other question, Thomas, is there a lot of opportunity for use of chemistry in this research you're doing for the chemists? Do you have chemists in Rio working with you?
not that we have collaborations with those
Okay.
and the chemistry. So interesting about chemical reactions which took place inside of because when we have but we have some and size versions And, we have others, some explanations for the position. We have used yeah, I have two questions. Very much for a very important many questions. In the interest of time, I restrict to two. One is a general question, the other is more technical. It's not general. Amongst your key questions, and the last point was aerosol radiative effects last time of that. What radiative effects?
You know that aerosols could, depending on the altitude height, it may reduce the quantity of solar light that comes to the surface. This is then that reduce it may result, depending on the location, on increase of temperature at specific height or decrease of temperature, for example, in the stratosphere. This is the direct impact, and also above in the mesosphere as well. This is then if we want to assess this very well, we need to have an idea about how this is the sphere, for example. And according to this, resolving this two-sphere radiative equation can assess how quantity increase. What could be the consequences in terms of circulation?
Okay, great. Can I ask my technical question? Yeah. So you mentioned that you can characterize types of sources using the sun photon. We have sun photon roof, right? Which is not in use.
But it was used in I presented here.
Yes, it's part of, but at the moment.
It's going to remember, Martins know there's going to take. It's a sensitive. It belongs to
Okay.
that fund.
I
And
will-
if it's still
I
there,
hope that it means
Let me look.
then
I wanted to ask.
Anyway,
I wanted to ask whether you have this aerosol optical depth. Then on the diagram you have also this AE.
Armstrong, which is determine the size of the particle.
I see. So that's this Armstrong exponent. Okay, I got it. And concerning the aerosol optical depth, can you shortly explain, just shortly, how you measure this?
You see the sun photometer. Yes. Okay. There is a no, yeah, this one. Yeah. You see, this is your sun photometer pointing to the track the sun. If there is aerosols here, the quantity of light that you will scan, it will not, it will not, it will be less. And depending on the quantity of aerosol you have here, the energy that it will be measured by the sun photometer will reduce. Then this measurement will give you an idea about the total quantity of aerosol between sun and the instrument. That's what we call aerosol optical depth. Because it tracks the sun and it will give you what quantity of aerosol you observe in this direction.
What is measured by measuring a clear sky, then measuring, you know, what that is.
what's the baseline value?
Yeah. Measure a clear sky, so you know that's much sun in the UK.
Because we do have the atmospheric situation down.
Without errors.
Yeah. Like baseline. Yes.
we'll have to wrap up. So Judy, did you have a question about the sun photometer?
No, we can go have a look, but then if it has gone, I can talk on. So if you want it back.
Bring it back. Okay.
Yeah.
I hope you can.
So last question from Ola.
know that aerosol density is usually affected by weather conditions. You take weather into all this measurement.
What do you mean weather from hygrometry?
Let's take
Elevation layers.
yeah, something like that, and perhaps also when you have something like precipitation, which reduces the density of aerosol once there's precipitation.
So precipitation is supposed to remove aerosols from the humid deposition. So after the precipitation, you will have less aerosol.
Is that the point I'm making? Does it have any impact with respect to
You see it.
you see the effect?
Oh, it's unfortunately there is a lot of curves we remove. That's why we can find, for example, the raw measurement we can have continuous measurement. The result when we do the tables remove all the data that we are very contaminated with that.
Because we've been having very bad students
Yes.
in the last few years, and wondering has that like washed out areas.
It's supposed that after the rain, there is the sky is very clear. And it's good idea. We can try to see what is the aerosols that's here just after every run. Good idea.
All right, last one.
Emmanuel, you're welcome to unmute yourself and ask a question.
Time for the question.
Okay, so if nothing is happening, we can wrap up.
Well, we can take other questions. There's lunch waiting for everybody. NITheCS talk, very generous of NITheCS. And I'd like to thank Mr. Hassan Bencherif and Mr. Nelson Begue very much for their talk.